How are you?
I'm so good. How are you?
Good. Do we have somebody who's going to do a prayer for us?
Dude,
Yeah, can
give
you
me
say
just a
dollar
second.
sign? Because it compiles, but it doesn't work. Do you think it has to do with the size of the image? How did you comment on it? Control L?
Is it already?
Go back side? The good one.
Yeah. All right. Bonnie's going to call on our prayer person.
Okay, so today we have Guy saying the prayer, whose favorite apostle is Moroni, and whose favorite Kettle's persona is Pseudo Gary.
Dear Heavenly Father, we are very grateful for the opportunity to be here today. We're thinking that all of us can get here safely. Please bless this class that we may feel the Spirit and we may also learn from Dr. Cattles. Please bless him that he may have the skills to teach us and help all of us to return home safely after class. We love you very much and we say this in Jesus Christ.
Amen. Thank you, Guy. Thank you, Bonnie, for coordinating. So, what's the news? Anything in your personal lives or anything related to class? The virus, the coronavirus, yeah. I hope. Is anyone else scared of getting the coronavirus?
No.
No?
Because it's the fourth plague we've been diagnosed with in like last decade.
Pandemics are a big deal. I'm sure if we watch some map, it's going to go across the whole United States and somebody's going to be miserable and end up in a hospital. That's not going to be awesome.
It's probably gonna be me just because I'm tempting fate.
So are we missing some people today because of the weather or?
Yeah.
And so I see people glued to their screens. Is that because there's stuff going on in Albrecht's class or what's?
Yeah.
Okay. Just trying to get a pulse, a read on things. So we should. I wish. I can. It's not that hard.
You are in control.
No. There's so much material. There's so much material that we have to get through in this class that it's not really feasible or possible. The good news is, for anyone who's not here, they can watch the video later. Okay. One of the cool things that I got to do recently, as some of you present know, I got to go to that Silicon Slopes event. And I got to hang out with the coolest people. All right, there's some of us. What? Oh, okay. Well, yeah, Zuckerberg, he was there. That was cool. He met all of my stereotypes, but then he made me like him on top of that. I think a lot of us came out with that. He really is a little bit robotic and like Data from Star Trek and stuff. I loved it when he called Eagle Mountain, Eagle Top? Eagle Rock, and then he just goes on to say, communication's not my strong suit. And he's like, let's be honest here, like something along those lines. It was pretty funny. And then then he went on to say, like, look, I was really excited about talking about my new data center, and I messed it up, and blah blah blah. So that was, anyway, it was interesting. All right, this is Spencer Hilton. He'll be one of our new instructors in future years. He sat with us. Some good presentations. Connor and I, we spent some time doing some good in the world. So that was awesome. You know, I got free tickets, free meals, all those presentations, but I got to give back. And I practically lost my voice talking to him, so I apologize that you have to listen to me again today for another hour. I couldn't help but notice all of the networking devices around. This is an Aruba device, like the ones, I don't know. Oh, that should be probably one right there.
Under a chair.
Pardon?
Under the chair.
That one's under the chair. And then I was looking at the cable. So that's the only way it gets power, so that's power over Ethernet, one of our newer standards for networking and stuff, that you can get power that way. Technically, your Raspberry Pis can run that way as well. If you're connected to a network interface that runs power over Ethernet, oftentimes there'll be like this one, here's a device that says power over Ethernet for these 2 ports. So if you connect to things that say power over Ethernet, that could actually run your Raspberry Pis without any other power sources. So yeah, I'm just geeking out looking at the networking equipment in the room. Isn't that nice? Some more friendly faces on the train. More friendly faces on the train. It's awesome, Jace. Where are you at? And then, like, one of the coolest things that happened to me the whole day was they were giving out skateboard decks, and several people waited in line for 45 minutes to get skateboard decks, which they knew I was excited about it, and so Jocelyn was the first one to donate hers to me. So, like, seriously, that is, like, the little kid in me is crazy excited about my free skateboard deck that I got via you. So thank you so much. And then Emma, is Emma around today? Okay, yeah. And Emma got one, and then she sold it, always the business person. And she actually negotiated. So tell us how that went down.
Some dude was like, you want $10 for it? I was like, 20. So I got 20 bucks.
She counters, says 20, and got 20 bucks. Yeah.
It was within 5 seconds of her getting it. Like, she got it, walked over to this dude, and like seamlessly handed it.
That is so cool. All right.
Do you have pictures?
Bryce, didn't you win AirPods?
Yeah.
I was.
Yeah! Okay.
It's froze.
Make it 20.
Are there the new ones? Were they the new ones?
No, not the max.
Oh, never mind.
that takes my snaps.
So I was actually going to bring the skateboard deck today, but I forgot. So
Maybe next time.
I'll try and do it another time. Pardon? Gary's got to bring it. That's true. Maybe we could get a picture of Gary doing some tricks on the deck. My ollie is still pretty poor, but I'm still trying. Okay, on to the other stuff. All right, so we've already been talking about Ethernet for a while. We're going to put a bow on this topic today, where it came from, how it works, MAC addresses. We've seen MAC addresses. We know that all of our network-connected devices have MAC addresses. We know how those are composed. We know that my wife turns the toilet paper around backwards, and that's not right. We know how we can use MAC addresses to have some fun and mess with our roommates or our kids or whatever. We started talking about the idea of packets, the fact that we have these naming conventions for how we send packets around in a network depending on which layer of the OSI model we're talking about. And so they have different names like frame, packet, segment. The idea being that if we start at the top, that our application, like a web browser or a web server, can package up some data that it wants to share with somebody else. We add in a bunch of headers, some additional bits on the front end. When it gets to where it's going, we strip those things back off, and then we have just the data that our application wants at that point. In terms of sizes, we might think of it in terms of the Russian stacking dolls. And so our biggest envelope, in a way, could be thought of as being the frame. And then we looked at the, one of the last things we did is we looked at the frames using Wireshark, and maybe just to have fun with that again for a second. Long pause. You guys can open up VNC too if you want. Okay, so I literally hit exit on there, and it took about 10 seconds, which is super annoying. Okay, so I had done a packet capture earlier, and so we see over in the left-hand column a list of packets that are streaming through. That now we talk about this by its name as a product name. which is Wireshark, but more generically, we just call this a packet sniffer. There's lots of different programs out there that are packet sniffers. So if you're using a program, it might not be Wireshark, but Wireshark is super popular. They all kind of do the same thing. You get a stream of packets coming in, and then it parses it for you and turns it into something a little bit more intelligible. So as I'm looking at this first packet here in the list that's going around, and I'm looking here where it says frame and Ethernet 2, so I'm looking at an Ethernet frame. I can see kind of in the summary box there, it shows me 7C, 2E, etc. is my source address, and then the destination address is the DC, A6, etc. Another thing with that I think is kind of cool, so this is kind of a summary of the packets, the OSI layer packets that are contained. This is the raw output that your computer uses to determine all the rest of this stuff. We can view this material down here as either hex pairs, or we can look at it as binary. At the end of the day, it's just one uninterrupted sequence of binary, in this case 98 bytes in length. If I come down here, okay, let me just show the synergy, or synergy is not the word I'm looking for, but just the, all right. Anyway, there's a word I'm looking for. So if I look right here, it says destination, DC A6 32, blah, blah, blah. Now, as I look at the raw packet data itself, notice that the first characters here are exactly what's there. So 1, 2, 3, 4, 5, 6 ends with CD. Okay, so that's the destination. If I click on the source, okay, if I click on the source here, it highlights the hexadecimal, the bits, the bytes that represent that. And so here it's 7C all the way through E1. So there's the second block of characters, and there it is represented. So that's kind of, I don't know, nerdy way, that's super cool. If I right click on this, I can actually view the raw data in different ways. Right now I'm saying show the bytes as hexadecimal. I can change it to bits. And so there are my, what should be my 98 bytes down there. So each one after another. And so again, if I were to click on, for example, the source MAC address, or the destination MAC address, these hexadecimal characters here are now represented in bytes. So 1, 2, 3, 4, 5, 6. 6 bytes, 12 nibbles. So, yay! We try. Okay. Yes, Kyle.
Wireshark is software that people use to watch passwords and.
Could you watch passwords and stuff in there? Yes, absolutely. So another thing I did not mention that I was planning on bringing out later on. Sorry, now I gotta wait the 10 seconds again to go back to my VNC. Okay, so you see the bytes over here, the binary. Over here, this is where oftentimes we see ASCII equivalents of what's over here. So if I'm viewing a web page that's brought down over a series of packets, I can see that information here. And so yes, if you did something in plain text like pass your passwords, you could absolutely view it in text, in ASCII right there. So now you know why it's so bad to pass things in clear text, because it's clearly visible to anybody with a packet sniffer. Okay, talking more about that frame, here's the overall idea of what's in the frame. I actually like this one better. We'll talk, well, okay, I'll start with this one. So we got some nice colors. We just saw evidence of the destination MAC address that shows up at the beginning of our frame. So there's a header on the beginning of our frame. We have a destination address, a MAC address, Ethernet type. So Ethernet 2 is, improved over the original one. Really, Yeah, the next part is the payload. So the payload is going to contain the text that you're actually sending around. So maybe this is your web page, for example. And the last thing on there is the checksum. So this is just a little mathematical calculation that you can use if you're a networking device to compare against the rest of the bits that came through. And if you get, for example, an odd number when you're expecting an even number when you run that type of calculation, then you know that something got warped as it came through, something got corrupted, so you just throw out the frame entirely. But what do you care about most for our class? Hey, there's a destination address, a source address, and then there's something inside that you actually wanted to see. And then just for the curious minds, imagine that you are a network. You're a network device like this. How do you know when you're receiving an Ethernet packet? It's just a stream of ones and zeros. And so think of it as a river crossing by. It's just endlessly streaming ones and zeros on the network as you plug in a cable and you start listening on your device. The way it knows that it's seeing the beginning of one packet versus another is aided by the fact that there's this thing called a preamble. So if you think about it, like, oh, this totally makes sense why they would make up something like that. So they do 56 bits of alternating ones and zeros, and then they do the last 8 bits with that sequence. So that way, if you're just, again, watching the bits go by, your device can go, aha, I see where to start, not just some random series of ones and zeros. The networking devices can say, oh, here's the start. I got it. Okay, so high-level idea, that's just what I want you to take out of it, that there's this idea of packets. Okay, some other information related to Ethernet that's important is these concepts. Broadcasting, collisions, the redundancy check, and then why we use switches now over hubs. So, I shouldn't show this slide. Too many words. the high level idea. I'll just switch to the next one so you're not reading them anymore. The high level idea with broadcast is just that sometimes one device sends something into one port and it wants to send that message out to all the other ports. And as long as you're on the same local area network, there's nothing that you can do to stop that from happening. Every single device can send broadcasts to all the other devices all the time. There are very good reasons why we do this. One of them relates to something called ARP, and I will talk about that later. Basically, it's just a way of making sure that everything can find everything else on the network. So there's constantly broadcasts going on to update the tables of information of who's actually on the physical network so that communication can take place. Whenever a broadcast is sent out, remember how this is the destination address slot that we saw before? What we have is a series of ones there, or in hex, all Fs. So this is a very magical address. Whenever a device sees all Fs coming in and says, oh, I know what to do with that, I'm going to send that same message out, that packet out to everybody else. Everybody's supposed to hear this. So that's it. That's the high-level idea of a broadcast. It's all Fs. See right there.
I fit all. Sorry.
All right. Next topic. So we're hitting these pretty quickly here. CSMA CD. Carrier sense multiple access collision detection. This is about the idea of what happens if two devices are connected and they both start talking at the same time. So if we're having a real human conversation and both of us start, especially on the telephone, what do you do when two people start talking at the exact same time? You stop. And then what do you do?
More aggressive one.
Yeah, I'm just thinking about our household conversations, you know. Yeah, people talk over one another sometimes. So ideally, if you think about how it goes down, is you both stop talking, you wait a random amount of time, and random is different for each person, and then one person starts again. You know, kind of goes like that. So basically, pardon?
I was just imagine doing that with Zuckerberg on the other side.
Yeah. So they thought, hey, that's a great system for how we will deal with two computers that try to talk at the exact same time. We can't mix our frames, you know. We got to have them delineated and separated. So they just thought, hey, that's a great idea. So what we'll do is, if there is a case where two computers start talking at the same time via the old model where you have that thick net connection that everybody's connected to. We'll back off around amount of time, and then we'll just have somebody start talking again. And if it crashes again, we just keep on doing that over and over. And if you crash too many times, you just give up and say, I'm not talking anymore. So, all right, that's it. That's carrier sense multiple access collision detection. Inherently, as part of the Ethernet standard, it had the capacity with your network devices to know if two devices talked at the same time, and it had a way to remedy that problem. Okay. Yes?
What was the name of that again? The name of the solution?
Carrier sense multiple access collision detection. And a similar thing happens with wireless networks. It's carrier sense multiple access collision avoidance. So they use everything in computers, as you go back to the beginning of time, they just kind of take like one theme and then they just like repackage that idea a little bit. You'll find that a lot the more you spend time with technology. So yeah, so with wireless networks, it's almost the same. You actually don't start talking at the same time. They actually request permission to talk. And if you get permission to talk, then you talk. So they actually you don't ever collide, you just wait for your turn to talk. So I guess wireless networks are a little bit more polite in that sense. Okay, error detection. Okay, I've got that. Okay, yes. So I think you get the big idea already that sometimes data can get corrupted as it's going across the wire. Why does data get corrupted typically? Noise. Where does noise come from? Sure. Categorically, I was going to say the physical world. So the physical world. So you have this perfect digital world. The physical world introduces interference, and so sometimes your bits get mixed up, and then they don't come out in the way that they were intended to be. I'm going to tell you something a little simpler for a second here. So I remember way back a long time ago, as we talk about ASCII, if you look at your ASCII table, it so happens that as you look through lowercase a through z and uppercase a through z, so basically all your alphabetic characters, that's all contained in 0 through 127. So it used to be that when you had 8 bits, you know, like 1, 2, 3, 4, 5, 6, 7, the last one was the error check. And so the real simple thing that they did when they're communicating is they would just add all these things up. And if it's an even number, they would make this a 0, and if it's an odd number, they'd make it a 1. So for every receiving device, they would look at that series of numbers, seeing if this this flag here that indicates whether it was supposed to be an even series of characters, an even total or an odd total. If it doesn't match up, it then just drops the byte. I didn't go over that too fast, did I? It's like easy idea. So there's just these simple ways, these little tricks that you can use to see if your data got corrupted. So an Ethernet packet is larger than a byte. It can be around 1,530 or so characters. So there's its own special math for how it determines if there was corruption. It does some. You probably saw in the book there was this interesting math that they did that allows you to come out with a series of characters. So rather than one character, you get a series of bytes at the end, or bits rather. And if it comes out the way you expected, then it's a good frame. If it doesn't come out as a bad frame, then you just drop it. I don't think it would be useful to actually do this math on an exam or anything like that. The bigger idea is just that, oh yeah, it totally makes sense that regardless of which layer of the OSI model we're talking about, whether it's a frame, whether it's a packet, whether it's a segment, it's possible that some type of physical world problem could happen, corrupt the packet, and we need a way to check for that. And we know that there's some simple things that we could learn that would allow us to do the math by hand, but it's not worth it. Just know that there's a way that it's done, that does happen to correct and discard bad packets. Yes?
So, how does the receiver know what to expect as far as the bytes go? Because you say that they both have like the series of bytes and you check them against each other, right?
So as part of the packet, the last the last few characters are going to be some numerical number that sometimes we'll call the checksum, maybe in a different context. So it's just looking at the totality of the packet versus the checksum. It runs its procedure every single time on the core part of the packet and see if the checksum matches. So for every single frame that comes along, it's got the two things and it just checks them against one another over and over and over again. Okay, so when I started last time, I talked about the big picture. Does anybody, no, I said the big picture with respect to the network designers. So does anybody remember what the big picture is with respect to the local area network designer? What's the big issue that they care about as it relates to all these technologies related to the LAN? Okay. I don't know if I should be upset or, it's okay. I'm going to say it again right now. Okay, go ahead.
Was it
Congestion, perfect. Woo. Nobody does it like Sherry. All right, right on. So, yes, the issue is congestion that's going to happen. Okay, one of the things I talked about is broadcast. All the time, devices are broadcasting. You turn on your network packet sniffers, you see tons and tons of traffic going around, particularly related to broadcast traffic or just legitimate traffic. Maybe you could have every single person on there watching a YouTube video. The more packets that are flowing across, eventually you bog down, the capacity of a particular network to carry data. So let's talk about how we deal with that to try to fix that problem. Do you remember that Dr. Albrecht on his first day said, at least in one of the sections I sat in, he talked about how sometimes in technology, they just make up a solution to a problem. And that's what Ethernet is. Like, how are we going to communicate in a local area network? Well, we just talked about CSMA, collision CD. We talked about what do we do about collisions and error checking and all this other stuff. So we just make stuff up, and then sometimes our solutions are not really perfect in retrospect, but it works. So I would say the same thing, with the passage of time. It's wonderful, it's a miracle that we got this to actually all work, but we look back on it and we're like, for the modern era, there are some problems with how this originally worked in terms of the efficiency and the congestion that happens. And so these days, we kind of put in a bunch of little fixes and tweaks to try to make our networks work a little better, given that we're still using old ideas. So here's kind of some of the changes that have happened over time. Over here in the upper left, this is our original idea of things. We have that bus, that physical cable, that thick net that everybody's connected to. And in terms of broadcasting, in the original case, regardless of whether it was a broadcast message or just a plain message from computer A to B, every single device on there sees it, which is a problem when we get up to about 255 devices on there. That's a lot of talking and messages that not everybody needs to know about. Later on, we went to a different physical topology where we have this device over there. This is not a hub, but this looks like a hub or a switch based on the ports there. This is actually an integrated device that contains a switch in it. But we'll just pretend that this is the hub for a second, because the hub just has a bunch of ports on it. So later on, after we went from that physical networking equipment, we went to this physical networking equipment where we used Ethernet cables attached to computers, and this thing in the middle was called a hub. While physically it looks different, and we would call this topology a star schema, logically the way it communicated to all the computers had not changed. It was still identical to that. So our second generation of equipment meant that if computer A wanted to send a message to computer B, the hub would broadcast that message out to every single port on there. Is that very effective? No. Okay, so our next generation, which looks identical but just has a different name and technically a little bit different hardware inside, is called a switch. And so for those of you that picked it up in the reading, what's the difference between a hub and a switch then? Spencer?
Well, a switch basically analyzes the packet coming in and determines where it needs to go.
Yeah.
So it doesn't broadcast to everybody, then have the computer decide that this sends it to the right place.
Yeah. So as different devices are as different computers are talking to one another, it keeps track of who's who, and it says, oh, I know who that message is directed towards, and it just kind of creates virtual paths between any two devices, and that has a tremendous savings in terms of the throughput that's possible in a device like this. However, there is still a problem. The problem is, based on the standard of Ethernet, if you send in a broadcast message, so you come in one of these ports and you're not going one-to-one, but you're saying, I want to talk to everybody, by rule, the switch still has to send the FFF incoming destination addresses out to everybody. So the switch is awesome because it reduces a lot of traffic, but Ethernet is still problematic because of the way broadcasts work. All right, so last two slides on Ethernet. All right, almost out of the woods on this one. So if I look at so oftentimes in terms of networking, we talk about the broadcast domain with the implication that, hey, these 111 or these F broadcast addresses cause a lot of problems and congestion on the network. So we talk about our broadcast domains, and so here I have H3 as a computer and H1 as a computer, and they're separated by switches. If H3 does a broadcast, it gets propagated through a whole bunch of daisy chain switches, potentially. If nothing else is done, any message broadcast from there will get cascaded and sent out to every computing device that's connected in the network via a series of switches. So in theory, we could probably go way bigger than 255 devices. And that would be just a nightmare. So that's a problem. We would like it if maybe we could restrict our broadcast messages to a locale that makes sense to us logically. So, introducing the router. So the router, one of the things it allows us to do is segment off the broadcast messages. So if this thing says, I'm going to send a broadcast message to everybody in my network, it's going to get to here and it's going to stop. So if this is connected physically to 100 other devices, the message will come through here, hit 100 other devices, but it will not propagate past the router. So we now have this thing logically divided because of the router into 3 different broadcast domains, meaning any broadcast that originates in this domain, separated by the router, is going to stay in that area, in that local area network. Yeah?
In which case are you creating a network? Are you creating a network between the computer and the switch and the router, or just the computer and the switch?
Okay. Tell me if I'm answering your question or not. Conceptually, these are 3 different networks here, and conceptually that's one network. Another way that we define routers is they separate networks. So we actually usually, what we do is we actually do a slightly different addressing scheme in each of these areas to help the router distinguish where traffic goes and stuff like that. So in addition to this formal definition of we segment our networks via a router, it also, as a side benefit, reduces broadcast traffic, which means our network is going to speed up. So if you were a network consultant and you're coming in and people are like, hey, I'm not able to get good internet access, what's the deal? These are the types of things that they're looking for. And then they laugh at you. Because they know their stuff and they're like, oh, that's so silly that you did that. And, you had one big broadcast domain, but I know how to fix this. So now you know what they're doing. Okay, last topic, the idea of VLANs. So in addition to routers, there's another way that we could segment our broadcast traffic, and that is creating something called VLANs. So physically speaking, it looks, let's just kind of go through the picture here. We have 9 computers. These 9 computers are all connected one with another via a bunch of switches that are also connected with one another. So without any other configuration, this setup, this diagram right here, means that any computer doing a broadcast, it gets propagated to every other computer on there, which is bad. But switches are programmable. So what you can do is you can say anybody plugged into so it's just numerical. You can say anybody plugged into this port is part of VLAN 1, and anybody plugged into this port is VLAN 2, and this is VLAN 3. And so what can happen then is when you do a broadcast within a particular VLAN, it's restricted to that VLAN. So this is a little bit weird conceptually. We have a whole bunch of different devices like these that are all connected to one another, but it's reading the VLAN tag, and it said, so rather than just doing the broadcast to everybody, broadcast in VLAN 1 only end up going to VLAN 1. Broadcast in VLAN 2 only go to VLAN 2. So VLANs are also a very popular and commonly talked about way of dividing up your networks to control your traffic. So if this is tagged as VLAN 1, 2, 3, even though they're on physically different floors of a building, the way it works out is the broadcast through the switches is smartly controlled, so it only goes to the group that it's supposed to go to. Okay, any questions about Ethernet stuff? Okay. This is where we've started to get a little deep. I feel like on some of the previous topics where I've said on the exams that I'll ask you questions like, how can you differentiate between different hardware components on a computer? It's kind of a little bit light and fluffy and easy. This is a little bit deeper stuff. So let's just review here. If I go out to the content portion of the website, there is a review guide here. So let's just see how what we just covered as it relates to Ethernet corresponds with the study guide for the exams. And see if, by virtue of our classroom experiences, are prepared to answer those questions. So, Ethernet. Can you draw a diagram of how Ethernet communication works? And that one's probably a little tricky, but I think you can do it. But here's maybe some more fundamental questions. What's the role of MAC addresses? If you guys discussed this in your study groups, I bet you could answer that. What are the two parts of a MAC address? What is the difference between routers and switches? What are the different types of packets, datagrams called, and what OSI layer are they associated with? How does CSMA CD work? At a high level, how are errors detected when a frame gets corrupted? So based on these questions, these are, you're going to find corresponding problems in exams. So you can probably focus your attention initially on the slides and what we did there when I post them. The book material and stuff is helpful and was good to get you a start on things, but hopefully we kind of made things concrete as part of our discussions. Yeah?
Will the exams be like multiple choice stuff, or is it going to be short answer?
It's going to be a combination of both. Okay, so jumping on to the next topic. I'm excited to talk about IP. Stuff. Yes. Okay, we've moved through one topic. And by the way, just be strong for the next couple weeks. As we get through this week, we're going to do IP and routing. Next week, we're going to do some stuff that revisits some of the things that we talked about as we combine some concepts related to IP and layer 2, the data link layer, Ethernet. We're going to talk about some of those topics and refine and add on a little bit of to those two topics. That's a lot of concepts. It's a lot of stuff to get through. Once you get through that, I think everybody feels a little bit more comfortable when we start talking about the application layer. When we start talking about things that are more familiar to us, like how do web servers work, how does email work, and stuff like that. So it feels a little bit more comfortable. So just get through 2 more weeks of these concepts and difficult things, and then it'll feel a little bit more comfortable for most people, I think. Okay, for our 7-layer beam dip OSI model, we've gone through physical, we've gone through data layer, now we're going to be talking about networking, where IP resides. Okay, we already know the answer to this question. What does each of these have? Which is a MAC address. And here's my next question. Guess what these also have? They also have IP addresses. How is this possible? I'll talk more about different networks as well at a later time. Okay, so I'm going to revisit this idea a couple of different times. You might think about your MAC address as kind of like your DNA sequence. It's just stamped into your networking card. It's something that stays with it permanently. Your IP address, has anybody ever been over to, is temporary and reassignable? Has anybody ever been to Rancho Markets? Anyway. Rancho Markets has some good meats that you can grill up over there that are marinated.
So when I go over there and I get in line and everybody's speaking Spanish, to me, they're like, yeah, we don't care that you're in America. We're speaking Spanish to you because you're in this store. You pull a number and you wait in line. That's kind of like the idea of an IP address. You still have your unique identification with your DNA, but temporarily you are assigned this number. This number allows you to be identified. Okay, let's talk about some other things related to IP addresses. IPv4 version addresses are laid out like this. The first number can be between 1 and 255, the second one between 0 and 255, etc. for the next two placeholders. So there's your range of addresses that are possible. You should not see things out. There's no such thing as a valid address, for example, that's 1.1.1.256. That's not possible. It doesn't exist. So we've bounded a little bit what an IP address is and what it can be. Okay, so this is a part that I'm actually excited to talk about, do some storytelling a little bit here. There's the nuts and bolts of it, like how this works, but then there's also a kind of a fun part to this, which is kind of conceptually why things exist and what people were thinking about. Okay, so, bet you didn't see this coming, Captain Moroni. So Captain Moroni looks good. As part of the war chapters, one of the things we pick up on is that communication is a key to victory. Would someone read through this scripture for me? Who would want to read this real quick? Please, Kyle.
Moroni also, knowing of the prophecies of Alma, sent certain men unto him, desiring him that he should inquire of the Lord whither the armies of the Nephites should go to defend themselves against the Lamanites. And it came to pass that the word of the Lord came unto Alma, and Alma informed the messengers of Moroni that the armies of the Lamanites were marching round about in the wilderness, that they might come over into the land of Manti, that they might commence an attack upon the weaker part of the people.
Okay. So I love so many different parts of that about this. I love the fact that Moroni, being one of the most famous people in the Book of Mormon, is, and this great war leader is like, hey, I need to know the answers to something. I need some answers from God, and I know who to get it through. I'm going to go to the prophet. I just love that. And in this case, the people of Nephi were about to be attacked by the Lamanites. Was it important that this message was received?
Yeah.
Yes, lives were saved. Lives were on the line based on this. Similarly, we had the same thing happen with Ammon, the arm separator. All right, who could read this one for me? Whoever wants to, just jump in. Okay, Jocelyn, go ahead.
But the king said unto him, the fire of the Lord, he saith unto us, go, we go, otherwise we will perish in the way. And it came to pass that Ammon went and inquired of the Lord said unto him, get these people out of this land, that they perish not. For Satan has great hold on the hearts of the Amalekites. We do stir up the Lamanites to anger against their brethren to slay them. Therefore get thee out of this land, blessed are this people, this generation, for I will preserve them.
Awesome. So this was in reference to the anti-Nephi Lehis who were willing to lay down their arms and suffer death rather than fight against their brethren once they'd repented of all the bad things that they'd done. Again, how important was a message from the Lord? I mean, were lives on the line? Yeah. So they got themselves out of there and they saved themselves. Okay. Communication is also very important in modern warfare. We have lots of different devices that we connect to through data communications, and it's a strategy and a tactic throughout history that if we can disrupt communication lines, we can win wars. So here's something that you probably didn't know about, which kind of underpins a little bit about why IP exists the way that it does. So this is a map of the interstate system in the United States, and many of us probably think about the interstate system as a fine way to travel from coast to coast and visit national parks and stuff like that. But notice the name up there. It's the System of Defense Highways. From the government's perspective, from the Defense Department's perspective, they need ways to move tanks and people and guns around. And if you knock out roads, then you could potentially win a war. And so
so the reason why there are many paths through here is because we need redundant paths to get through from A to B. Well, the same organization that put together the defense map of highways, system of highways, also put, so we have the DARPA, Defense Advanced Research Projects Agency. They designed communication networks to be the same way, such that if you were to lose one, so this is the original diagram of the internet, such that if you lose a path, like let's just say that we needed to go from, I don't know, USC over to Carnegie Mellon. If we lose a path here, the government wants us to be safe and be able to continue to communicate. If we lose a path, and we design this right, then we're still good. We have a redundant path.
Let's put the crossover in the middle then.
What's the, I don't know.
It looks like a weak point to me, I'm just saying.
Yeah, well, that is something good to think about. But that was just the original design. Like, I'm sure they were happy just that they got it working back then. Since then, we've got a lot more redundancy. But this was just a start. Okay, so anyway, I think that's kind of neat. That was kind of their thinking about it, and that's why we have all these routers and what are going to end up being redundant paths. Next time, we're going to talk about routing itself and do it in kind of a fun way. So as I talk about bunkering down for the next 3 weeks, the good news is that next time, we're going to kind of have a fun light day. We're going to kind of do an activity in class, because we all need that. We can't just like be doing this stuff, this kind of material all the time. Too conceptual. So we'll have some fun next time, but it still applies to routing. Okay, back to the hard stuff. All right, so if this is a conceptualization of a network, we have over here a local area network, another local area network, and then we have the internet, which is going to join us. So remember our Robert Metcalf, he helped us design the Ethernet technologies that work out here, and then DARPA allowed us to have these technologies that connect us from many different points around the world through redundant paths. Of note, you get private IP addresses on a local area network. You get private addresses over there as well, and chances are it's a repeat. Just like right now, if you look at your device, you're on a 10.0 address scheme. They got some 10.0s over there, and they probably got the same IP addresses assigned over here. What's going to be unique, though, is what's in the center. So these are public IP addresses. These are not going to be duplicated. So as we talk about private and public IP addresses, these are the ranges of private IP addresses. So as you're doing your security class assignments and stuff like that, rootkit and whatever else, if you see addresses that fall in these ranges, you know where the traffic is happening, which is on a local area network somewhere.
What's 172?
Pardon?
I just never knew about 172.
Yeah. So basically, if you jump on any local area network, it's gonna always fall within one of these three ranges. And then for the public internet itself, it's gonna fall in these ranges. So these cannot be duplicated. There should only be one and only one of these, so that we can address ourselves and find ourselves in the world wherever we're at. But on our local area networks, we reuse these all the time. Jacoby.
Are these classes the same classes that we read about earlier, where they were given to different size groups, or I can't remember?
Yeah. So I think that the idea of classes is a little bit less important now than it used to be. But the idea was that, so if I look at this range, there's about 16 million. So let's start on the private side. Same idea applies over there. If I start over here, there's like 16 million addressable addresses in here. There's 65,000 in this range, and there's 256 here. The idea was that depending on the size of the organization, you might need more addresses to give out than others. That's at the high level. And maybe I should just stop there. But yeah, that's kind of just the same idea with those ranges as well. As we go to the higher level ones, you can give out more addresses to a group. I might talk about it more later, but for now, that's good enough. Okay, so let's look at some addresses in the wild right now. If you want to, you could look at your local device through a terminal window or your Raspberry Pi. Okay, so here I am over on my Pi. I wonder if any of my windows are bigger. There we go. That one's good. Yay. Okay, so I type in ifconfig, and I have mine connected physically to my wireless router as well as wirelessly to my wireless router. So it actually my Raspberry Pi actually has 2 IP addresses. It's got 192.168.1.248. So what's special about that address? At least its range. What's special about its range? Peter?
Yeah, it's a local area.
It's instantly recognizable as being in the range of private addresses. As I go down to my physically connected address, well actually, sorry, that one was the physically connected address, ETH0. As I go down to my WLAN, again, same thing, it's a different number at the end, and instantly recognizable as a private address. And just as a note, this 192.168.1.something is one of the most typical schemes that you will see for home network addresses. And so it will give out addresses between 1 and 254. Technically, there's 256 addresses available there. The first number and the last number are always reserved for special purposes within a network. I'll plan to talk about that later. All right, any questions on that? Okay. One of the commands that we often use in the networking profession is ping. Ping is becoming a little bit less useful, as is traceroute, as we get more and more secure over time. But for debugging purposes, this has been critical to figuring things out. So if I want to know, for example, am I connected to the internet, oftentimes what I'll typically do is I'll type in something like ping google.com, and I'm getting responses. Okay, and so we go from there, and oh, that's so messed up. It gave it back in IPv6. All right, I wonder if it'll do any. Let me try my local device and see. Well, okay, let's try BYU. Ping byu.edu. There we go. I like that better. Okay, so I'm trying to ping BYU, and immediately what I see here is it converted byu.edu into this address. Okay, so what is special about this address in terms of its range? It's within the public address space. So from wherever we're starting, we can send out some packet into the universe and let the routers figure it out. And because it's in the public space, eventually it will get found. Yeah, so go ahead and ping any of your favorite websites and see what their address is.
So with this public address, is this in any way related to what I've heard called a proxy server? You know what that is?
Yeah.
Is that completely separate?
The idea with proxy servers is sometimes you want to go through another server on your way to somewhere else.
Yeah.
So at a high level, going through a proxy server is going to disguise your IP